Great.
All right. Well, it's my great pleasure to introduce Dr. Geoffrey Tison today to kind of our AI forum. This is kind of someone that I've known Geoff for kind of quite a bit a while. We're doing a little bit of collaboration on various projects, and he's been incredibly prolific in essentially all facets of kind of AI and cardiology in many modalities, and kind of with work in echo and work with EKG and work with I think PLAT and kind of a broader vision of kind of what cardiology means and cardiovascular risk factors, as well as I think digital health. Geoff was one of the, or is the first digital health fellow was at UCSF, and really excited to have him come talk with us today. Dr. Tison received his MD and MPH both from Hopkins. Also, it looks like was an Osler Marine, so did residency at Hopkins and then moved out to California at UCSF for fellowships in cardiology. Is kind of has an echo fellowship and has done a lot of work in digital medicine. So I think that we're really excited to hear about some of the work that he's working on, and really excited to have you here, Geoff.
Cool. Thank you so much. Yeah, thanks, David, for that generous and great introduction, and thrilled to be here. Wish we can eventually do this in an in-person forum. I'd love to meet y'all in person. And I grew up in Southern California, so it's home in a way. So I would, hopefully we can do this again soon. So yeah, thanks for having me. Happy to be talking today. And obviously there's a number of different sort of topics that we could cover, but I figured I would try to focus my talk on one of the things that, I'm excited about for the field in general. And I know that a lot of folks are thinking down similar lines. So this is by no means sort of a novel construct, but I think it's just one way to organize the work that some of the work that we've done, as well as, of course, work that other folks have and are doing now as well, including in this group. So I've titled my talk, Finding New Meaning in Familiar Tests and Expanding Our Diagnostic Toolkit with AI. And I'd like to, please feel free to jump in, ask questions as it goes if they come up, because I'm happy to explain things in more detail. And I'll try my best to leave some time at the end to try to open the floor for discussion, because I think given that we're all in the same field and domain, that might be some of the most fruitful parts of this. So please feel free to jump in. Here are my disclosures. So just to start with a little bit of motivation, not that, again, it's really needed for this group, but it's no surprise to anyone that there is a lot of data in medicine. Of course, classic data that everyone's familiar with, like ECG data, echo data, lots of imaging data. We're starting to get, of course, some continuous monitoring data that are increasingly in clinical use, by physician prescription. And then, of course, there's this whole other world as well of our smartphones and smart sensors or remote sensors. So all this is to say that there is increasingly large amounts of data in medicine. This is from a now getting older review of data in medicine in 2017 in JACC, and this is not exhaustive, but they attempted to kind of list out the different types of data that might be available, as well as the categories and then the links between them. So this is just kind of a visual to suggest this idea that indeed there is a lot of data. It's going to be heterogeneous between patients or amongst patients. They're not necessarily going to have all the same available data, but there is a lot that we could potentially try to leverage. And so how can we better utilize this large ecosystem of data? And what are ways that we can potentially glean more information from existing tests? That's sort of the theme for this talk. Now, given that this is the forum for AI in medicine, I think everyone here is likely on a similar page that amongst all these different kinds of data, AI and machine learning tools can hopefully play an important role in helping us make sense of this data. Now, from a clinical perspective, as a cardiologist and clinician, this is what I would identify as at least one of the motivations for applying AI in this way. So how can we use it to try to assist physicians? So from the clinical perspective, I think most clinicians here would agree that we, at least most of the time feel like we're behind, that we're kind of inundated with a large number of different kinds of traditional medical data that we need in order to make decisions. And then, maybe a patient now comes in with a 23andMe genetic test or another commercial color panel or something that, there are startups that are kind of doing these different tests, and without sort of guideline-based recommendations by which to interpret this, it becomes a bit hard for us to really do much with it, at least currently, right? So it sometimes feels like we are, as clinicians, asked to be these data processing machines that are always trying to play catch up, and that there's less time kind of for the fundamentals of doctoring. So I think one of the visions is that potentially AI and ML can serve this role to help us try to integrate these many different modalities of data and ultimately improve the way that physicians can provide care. Now, luckily, there's been a growing body of great work that has been done and will continue to be done, demonstrating how AI can do this. So how AI can analyze different types of medical modalities in order to, at first pass, derive inference or conclusions that clinicians and human physicians can currently do. So things like identifying pneumothorax from X-rays. This is work that I was involved in a little bit ago, looking at different arrhythmias from ECGs. And there's been a lot of work done. There's still a lot to do, and I think this is a lot of what will initially impact the way that we deliver care. Is hopefully these types of algorithms will continue to be developed across the panel of clinical needs that we have, and there's hope that this can help us as physicians standardize the process, potentially provide an ability to do systematic QI for different tasks, and ultimately, of course, try to just help us do our jobs better. That's the goal. And in the best version of the story, this provides more bandwidth for doctors to hopefully do more of the doctoring that we're getting less and less time to do. But for this talk, I'm going to specifically focus not on these studies specifically, but on studies that have as their goal to try to use AI to extract new types of information. So to try to extract information that clinicians currently don't necessarily rely on, say, an ECG to do, or an echo to do, or an X-ray to do. And again, this is more of a method of organizing the work rather than kind of necessarily a novel construct, because I know that there's a lot of people in this group and elsewhere that have done things like this. So I'll start with a few examples from work that we've done. And again, kind of to just describe some of the ways that we're thinking about how this can be applied. So this is, I'll start with this paper that was published a year and a half ago now, and in Circ CV Quality and Outcomes. And what we aim to do here was really create a broad-based platform by which to analyze ECGs, number one, but also identify human identifiable ECG predictors that could help interpretability for these model-based diagnoses. So we wanted to specifically accomplish both tasks in designing this platform. So in order to do that, given that the ECG is highly studied, and there are segments and interpretations physiologically of what each of these segments and durations mean, we wanted to try to maintain that integrity as units of analysis for the algorithm. So the first step in that was to try to segment the ECG into those meaningful segments. So things like the P wave, the QRS duration, the PR interval, things like that. So any cardiologist or physician can kind of describe what those mean. Now, I will say to this machine learning group that, like, by doing that, we are imposing a constraint on the algorithm effectively to essentially forcing it. Well, it depends, I guess, on how we input this or what kind of algorithm we ultimately use, but kind of forcing it to use each of these segments as its smallest level of analysis. So that is an acknowledgement that was a sacrifice we kind of made in order to achieve this interpretability. So because we are ML people and not necessarily signal processing, we're not a signal processing lab. We actually applied a neural network in order to accomplish the segmentation. But there's a lot of algorithms out there to try to do this in other heuristic-based ways. So we did this because this was the tool that we were most familiar with. And then from that segmentation, we then essentially sampled the ECG from those durations and intervals, which have, again, physiologic meaning. So we eventually created a 725 length input vector, which was essentially rationally sampled across each of these meaningful segments and durations. And we actually did sample, for example, the raw voltage numbers of the QRS interval, right? So this was a sampled raw voltages rather than just like the onset and the offset of the QRS, for example. So then we ended up with this representative vector for every single ECG. And from there, we were left with a few decisions as to what kind of final classifier or regression model we wanted to use. We chose a gradient boosted model, in part for the balance of performance and explainability possibility. And so, for example, we use this to classify disease. We could also then use it to do regression, which I'll talk a little bit about. And so with this platform, we applied it to a number of different diseases as a means of demonstration. So pulmonary arterial hypertension, hypertrophic cardiomyopathy, amyloid, also MVP, which is not shown here, showing that, at least for discrimination, we were able to achieve pretty strong discrimination for each one of these diseases. Now, for the non-clinicians in the audience, it's worthwhile saying here that if you hand a clinician or a cardiologist an ECG, they would not classically be able to easily tell you, whether or not there's PAH or HCM or amyloid from that ECG alone. It's just not something that we are trained or really understand can be reliably done. Sure, there are, if you look it up in the literature, there are a number of papers for any disease that have identified features that have been, manually identified in a cohort of 50 or a cohort of 100. But it's not something that most anyone, unless someone is a specific researcher in HCM, they might try to pick out those individual features from an ECG. But this tells us that there is a signal to try to do this from an ECG. So this is kind of down that theme of predicting things from given existing data that current medical practice doesn't try to do. Now, again, because we didn't just want to achieve strong performance, we also wanted to identify the contributors to each disease prediction. This is just a demonstration of applying that. So highlighted here in the colored bands are essentially variable importance from the gradient boosted model from each one of the segments, divided up into 5 portions for each segment. And more deeply colored bands suggest the segments that had higher variable importance. And we just plotted the top 5 or 6 or so for each disease. So for example, you can see that in PAH, the QRS, the early part of the QRS in lead V1 specifically, as well as the mid part, both were important. The large S wave in lead 1, for example, was important, et cetera. The QRS duration found, actually, when we plot the durations here, this is just QRS duration in general, not specific to a lead. So the QRS duration in general. Now, again, if you kind of dig into the literature and see what has been reported from these cohorts of 100 or 150 or so, you'll see that there has been demonstration that like the QRS, the large R wave in V1, is associated with RV hypertrophy, PAH, et cetera. And so this is sort of a nice corroboration of like what has been seen in the literature over decades. But of course, as you would understand, this is all data-driven, right? These variable importances were identified just from the data agnostically, without programming necessarily these segments as being important for PAH. And then, of course, the same thing for HCM. You can see here, I won't go through all the different segments, similar for amyloid. So the platform as we designed it was designed to do not only classification regression, but also to identify in that process the segments that were the most important for that task. Now, work has been done by multiple groups at this point for each one of these specific diseases, not using this platform, but a lot of these using end-to-end neural networks, and essentially corroborating the idea that there is indeed signal for each one of these diseases from the ECG. Now, I mentioned that in addition to classification, we were able to use the gradient boosted model for regression, as it is well known to do well. And so just again, as a demonstration for the platform, we applied it to a number of different metrics. And these metrics were all measured by echocardiography. So it's sort of the non-invasive gold standard for most of these measurements. And again, we were trying to use the ECG to predict these echo metrics as coded continuously. So for example, we showed that the ECG could indeed predict left ventricular mass index in grams per meter squared, which by no means is something a cardiologist would attempt to do by looking at an ECG alone. And then similar thing for mitral annular E prime. This is a Bland-Altman plot, and of course there is systematic bias here where we're overestimating low numbers and underestimating high numbers. And this pattern it tends to be what we see in my experience in a lot of actually regression tasks. But this is there is signal here. This is not randomness, even though there is this systematic bias. And so again, this is a demonstration of trying to do something with an ECG far beyond what a cardiologist could try to do, estimate left ventricular mass or mitral annular E prime, which is a metric of diastolic dysfunction. Now, when we dichotomize these continuous metrics, we show dichotomous classification of left ventricular hypertrophy, which is related to LV mass, and diastolic dysfunction. And this, at least, the binary classification of LVH is something that clinicians are used to doing, and there are a number of manual criteria by which to achieve this. So these two are not really surprises, but sort of help quantify how this did overall. And then similarly to the other examples, we can also see the segments that are important. So just to dig in a little bit to this, I won't spend too much time for the sake of time, but the vision here is the hope that we can do some degree of data-driven discovery with platforms like this, to identify new features that have physiologic meaning that might be associated with given diseases, right? And so I sort of mentioned that these markers of RV hypertrophy, right ventricular hypertrophy, like the large R wave in V1 or the S wave in 1, these have all been previously identified in the literature as associated with RVH or right axis deviation or RV strain, for example. And so it's sort of helpful to us. It's sort of validating to us to see these come out as the strongest predictors because it jives with what we understand physiologically. But then, of course, there are these other predictors that aren't as well described or not described at all. And so depending on the strength of the model, ultimately is how much weight we should put on these explainability techniques. But this performance was pretty good. And so it raises the question, what do these PR intervals, these PR segments, why are they coming out as strong predictors, and what could they reflect physiologically? And so potentially this could represent RA enlargement. There is a number of studies that have shown, let's see. Yeah, a number of studies that have shown that the PR interval is associated with RV area and diameter as well as RV diastolic dysfunction and RA dysfunction. And so, these are entirely hypothesis generating, but again, if the model is strong, they might point towards a physiologic basis, either electrophysiologically or structurally, that might be worth investigating further. Any questions here at this point? I'll just pause for a second.
Geoff, one question I always have, and I think this is a little bit more open-ended, but how do you, what's your framework to determine kind of what targets to go after, right? What's like a realistic thing that we can capture more information that kind of essentially clinicians don't understand, but their signal, and
Yep.
what's something that's could be reasonably described as unrealistic or not possible to do with AI?
Do you mean about trying to identify new features in a data-driven way? Is that what you're referring to?
Yeah, or like, obviously I think that PH, kind of HCM and amyloid are great targets. They're very clinically meaningful and it really impacts patient care. But where's the upper bound of that? Like what is a reasonable target for prediction? What is an unreasonable target for prediction? We're already seeing
Sure.
many examples of where it definitely already goes beyond kind of human interpretation. But there has to be something that maybe AI can't do, or it's much more in the noise than the signal.
Yeah. Yeah, I don't know. I don't know exactly how to answer that. I mean, I'll say that I've been surprised personally in a number of different cases. One of which we'll talk about, coming up, but is just the diabetes prediction. So I think to some degree it's a healthy skepticism of kind of down the line of what you're saying, that this might be more noise than anything. But the other, to some degree, you have to also respect empiric um, evaluation, where you repeat it a bunch of times, you look at it in validation cohort, and there does seem to be signal there after a bunch of controlling for a bunch of factors and trying to identify spurious correlations. I mean, that was actually our path, as I'll describe a little bit, for our diabetes work, where there was a lot of internal discussion, debate initially of what are we actually identifying here, and is this just a correlation with beta blockers? Is this just a correlation with hypertension? But after controlling for everything we could think of, it really did seem like there was still an association there. So yeah, I don't know. It's kind of a balance, I think, right? Because by limiting yourself as to what you might go after, that is a constraint. That is an a priori constraint that can be healthy, right, from an RCT perspective, but potentially it's a human imposed constraint that the ML world has shown is sometimes better to not impose those at the beginning. But I'm curious what you think as well.
Yeah, I think it's well said. I definitely don't have an answer myself. That's why I think
Yeah.
it's an interesting question and one I think of often.
I think just that healthy skepticism, I personally try to espouse, where you see something, you don't just immediately run with it and kind of, blast it to the world. You really try to investigate and cut it as many ways as you can. And if it's still robust, then it might, it's something that's worth hopefully identifying. Yeah. So I'll keep moving. And I'll just identify or highlight another thing that AI can allow us to do, which is allowing us to quantify what previously has been a qualitative or binary type of assessment, right? So here, what we're doing is we're applying the PAH ECG algorithm to ECGs over time. Each line is a patient, and you can sort of see the PH score change over time, depending on, just change over time. Which, again, what does this necessarily mean? Well, we looked at, for this purple patient, for example, which start with scores below the threshold for pH and then go above. We just showed the raw ECGs here, and clinicians will identify that, in 2010, 2011, these look fairly normal, but starting in 15, 17, these look more abnormal. So the score correlates with our qualitative assessment of what's going on. And I'm putting this here just to highlight this idea that AI can help us quantify things that previously, were not as easily to quantify in this way. And this is some unpublished work, not actually from this pipeline or framing, but it's related, so I put it here. But basically, we're also showing that a ECG-based model for pH that was trained on pH diagnosed by right heart cath here at 0 months. If we look back and run inference on ECGs 3 to 6 months, 9 months, et cetera, in the past, there is still predictive power essentially to identify PAH. Sorry, this is actually pH, not PAH. identify pH, you know, up to 2 to 3 years before the actual diagnosis was made by the medical system. So this has, you know, significant implications with regard to potential screening, especially with a test as easy as an ECG. This is also some unpublished work to say that, you know, we've applied this to we have and will continue to apply this to specific disease states. Some of it exploratory, kind of like what you're getting at, David. But again, if it's robust, you know, it's worth at least investigating what that means. And so here we're showing that in addition to identifying MVP, as we did in that initial paper, those patients with mitral valve prolapse, that's MVP, which have complex ventricular ectopy, are clinically at higher risk of sudden arrhythmic death, which is obviously a terrible sudden outcome. So there's work in the field trying to identify those with CVE because we want to try to prevent sudden death. And so the question is can we take essentially a normal ECG without PVCs, without, you know, VT, of course, and predict CVE, complex ventricular ectopy, amongst patients with MVP? And we're showing that we can indeed with reasonable performance. We're in the process of trying to validate this in another system. And then, of course, another metric related to complex ventricular ectopy in these patients is MRI measured Blake gadolinium enhancement, which suggests cardiac scar, which as a potential origin for the ectopy. And we're also have achieved reasonable performance there to predict LGE from an ECG. And then again, with using that same platform I described, we're able to identify the segments that seem to you know, play the largest role in that prediction. So we have ST segments, QRS segments. A lot of these are QRS, ST, you know, regions that have again been identified as being important for CVE. I think the one predictor that's been identified in a cohort, you know, manual type of fashion was the T-wave inversions amongst MVP patients, and so that's coming up here as one of our strongest. Quite interestingly, these PR predictors, for example, when we remove from the cohort those patients with MR, this is now getting pretty physiologic, but these predictors go away, which is quite interesting because it just jives with, again, what we might expect, where MR can lead to atrial dilation, et cetera, that can lead to PR prolongation. And so when we remove those patients from the cohort, these predictors disappear, which is worth investigating because it you know, correlates with our physiologic understanding. So again, how can we use AI to help us get at physiologic biologic mechanism, and hopefully this platform is one amongst others that can help us try to do that. Now, there's of course down this broader theme of using AI to identify to achieve tasks that humans can't currently. There's been, of course, a lot of work, including work out of this group or the groups at Cedars. And I just highlight a few here that most of you are likely familiar with. So identifying future atrial fibrillation, screening for decreased contractile dysfunction, so LV dysfunction, which we've actually replicated, and I'm guessing multiple groups have, and looking at mortality. So there's a lot of work that has been done so far to use AI to extract novel information, and I think this is a very promising area, right? Because if we can do this, then we can hopefully obtain more information from existing medical tests. All of you are well aware of how difficult it is to essentially design a new test and get it through the FDA and get clinical adoption, which might be the hardest and longest runway for any of this. And if we can glean information from existing tests that surpass what we currently use it for, it's already in the pipeline. It's already in Clarity or our clinical systems, and at least theoretically, I guess it remains to be determined, but the adoption should be a faster loop there. So I'm going to switch gears for the second half of my talk. So I thought maybe I'll pause here as well and see if there's any comments. Cool. Well, if anything comes up, just type in. So for the second half, I'll kind of get into, again, down the same line of we are in this new world of smartphones and remote sensors and smart devices, of course. And I've actually never quite been an evangelist of digital health for digital health's sake. There's been a lot of interest, or there's been a lot of sort of frothy excitement, I think, about that, and maybe that's faded in the past couple of years. But it's hard to ignore the fact that the smartphone is in pretty much everyone's pockets, and there's been a number of studies suggesting that in emerging economies, that some people are actually more connected than they are through their smartphone by virtue of the fact that that's the main method of getting on the internet and being connected with people, compared to in so-called advanced economies where people have computers and sit at their desk all day. So it's hard to ignore the fact that there's a lot of potential. There's a sense that we might be able to democratize care or access to certain types of care with the ubiquity of smartphones, right? So this is not news to anyone, but the question remains: how do we best utilize this kind of information? Because the data that's obtained from remote sensors and smartphones is very large, continuous, messy, heterogeneous. So how can we do this? So back to this idea again. I don't want to be excited about digital health and remote sensors for their own sake, but how can they be used from a clinical perspective, right? And so the clinicians in the audience will be well aware of this idea that in our current medical system, it's changing a bit, perhaps with Zoom and COVID and accessibility, but nonetheless, we have this episodic medical system where a patient comes into the clinic for a scheduled appointment, I guess either remotely or in person now, and the doctor will see them. The doctor will kind of review all the different tests that are available, make some kind of diagnosis, prescription, send the patient on their way. The patient goes home and then comes back in 3 months, 6 months, 2 years, right? So it's this episodic approach. And most physicians, in the meantime, in the interim of the 3 months, 6 months, 2 years, don't have the bandwidth or wherewithal or tools, frankly, to really keep tabs on a lot of these. I mean, if we place reminders for ourselves, this patient, we review the echo in 6 months, like we might do that. But by and large, the only time we kind of assimilate all this information as the data processing centers that we sometimes feel like we are, tends to be right before the next visit, right? So it's this sort of suboptimal, episodic amalgamation of information that a lot of this information is actually being obtained continuously, right? So it's this vision that a lot of people have: how can we obtain more continuous information to try to render diagnoses and care in a more continuous fashion? Because if we miss out on that, then that patient ends up in the hospital, which is never good for anyone and is sort of a large expenditure for the system. And so this idea of, can we use remote sensors to fill in the gaps of medical care between these standard episodic contact points with the healthcare system, that it's hard to, I think it's going to stay that way. We're going to have episodic contact points. So how can we fill in the gaps with this type of information? And so it's somewhat with that in mind that the Healthy Heart study was started. It was started in 2013 out of UCSF in cardiology. I was not part of the starting team, but I've been involved with it from pretty early on. Last I checked, there was about 350,000 or so, users around the world. This is a diagram from just one of our studies that I'll talk about quickly. But so this idea that people can link their data, it's an electronic cohort study like ERIC or Framingham, that's entirely remote, based on the web, and people can link their remote sensors. And by virtue of that, we've managed to obtain, by this time, 8 years now, a decent amount of data from a bunch of different kinds of sensors. And so actually all the rest of the work I'll talk about is based on data ultimately derived from Healthy Heart or derivatives. And I guess it's also worth mentioning that Healthy Heart has now become the Eureka platform, which is NIH funded and is a broad-based platform to build remote, disease studies for any kind of disease or any kind of cohort. And there's over 30 or so studies on the platform now. So it's been pretty successful. So this was one of our earlier works now, 2018, where we wanted to see, what we could do with a large trove of Apple Watch data that we had in collaboration with this group Cardiogram in San Francisco. And so this was the earlier version of the Apple Watch before we actually had ECGs. So what it did have was a PPG signal, and Apple doesn't give access, or didn't. I think they still don't give access to the PPG signal itself. But what they did do is derive heart rate from that, and then we basically explored with the data we had in Healthy Heart as to what that might be useful for. And so ultimately, this is what the data looks like. The raw data is just a schematic, but it's effectively, heart rate measurements every 5 seconds or every 5 minutes, depending on what mode the watch is in, as well as accelerometer raw data. So how much movement is there on the watch. This is what the data looks like. And again, down this theme of like, how can a physician use this data? I mean, a physician would have a hard time doing too much with this, with a large vector of numbers representing heart rate, especially as it's measured. This is day 1, this is day 5, and the sampling interval changes. So this is hard to interpret for most clinicians. But what can machine learning AI help with? So we put it into a neural network and basically showed, and this was somewhat exploratory, that we could identify a number of different cardiovascular, related diseases with simply heart rate and accelerometer data alone. So hypertension, diabetes, sleep apnea, cholesterol. This particular paper compared it against various different models, but they actually most of them actually show a signal. Now, of course, one of the more interesting ones that we honed in on was diabetes, in part for its prevalence and impact. This here I'm just trying to show, what can AI then help us identify, right, from this raw types of data that is otherwise hard for humans to interpret. And that also goes for the PPG signal, as I'll talk about shortly. So this indirectly also led to another study, which is similar, where we took the heart rate and step count data and saw whether we could predict atrial fibrillation, which AFib is certainly something that doctors can identify from EKG like this. But again, at least at the time, and still now, the continuous measurement that the Apple Watch provides is not an ECG. It's these heart rate numbers just like this. So we showed somewhat early on, I guess, that we could identify atrial fibrillation from the heart rate numbers. We validated this in a cohort of patients coming in for cardioversion with good performance. We then tried to validate it in an ambulatory cohort that I'm happy to go into this if you'd like, but this is actually, we almost didn't put this in the paper because it's such a messy analysis, but we ultimately decided to just throw it in there. But I still believe that most people don't quite understand that this was how messy it was, and how much, from my perspective, the fact that it actually worked to an AUC of 0.7 or so that it was is actually pretty darn good. It kind of shows that there is a signal, because the biggest thing I'll identify is that this was self-report of AFib. So at the time that the heart rate measurements were taken, we had no idea whether they were in AFib or not. So it's just, it's kind of a suboptimal analysis that there wasn't enough room in the paper to really describe the nuances of. But nonetheless, I interpret this as being that there actually is a signal to do this, and it's been validated in the Apple Watch now, or the Apple Heart study and whatnot. So the studies I've shown so far kind of highlight this idea of, can we recognize patterns that humans can't, to try to fill in the gaps between our episodic medical care, right? To kind of complement this idea of using AI to automate medical tasks and help us do our jobs better as physicians. Now, the last study I'll talk about briefly is related to diabetes. So as most of you know, diabetes is devastating. It affects at least 451 million people worldwide. Half are estimated to be diagnosed. At least for type 2 diabetes, there's often a long-standing insidious asymptomatic period when patients have it, but they don't know. And that's exactly when the organs are being damaged, like the eyes, the nerves, the heart. But ultimately, because it affects the circulatory, the vascular system, there are multi-organ complications. Now, diagnosis is not difficult. It tends to require a blood test, but that, of course, requires contact with a medical professional. And so, especially in that phase of 20 to 45, when many folks aren't seeing doctors, that's kind of when this asymptomatic type 2 diabetes tends to come up. So ultimately, actually, from that first AAAI study that I showed, we saw this signal to identify diabetes from heart rate and step count. And so we piqued our interest as to whether we could do that better with a raw PPG signal. And there's a number of reasons why that came to mind. So PPG is commonly used in medicine to measure heart rate and oxygen saturation. It's used by smartwatches and devices to get heart rate, often that light on the back of the watch. It can also be measured by smartphones. By sticking your finger over the camera, you actually get a color change in your finger with every heartbeat, and that can be sort of interpolated to give us a waveform. That's a single wavelength PPG, different from the dual wavelength that's needed for pulse ox, as you've probably seen before. And so we get a signal like this, and the Apple Watch, of course, looks at the peaks to try to identify the heart rate, amongst other things. And I believe that Apple Watch now also does dual wavelength with SpO2. And so from a smartphone measurement on the camera, we were able to get raw data like this. And ultimately, so there are, a lot of signal processing work that's been done thus far that have identified specific features associated with PPG that might be of interest, right? So to look at heart rate variability, to look at different slopes, et cetera. So this is sort of the signal processing approach. So this has been interrogated quite rigorously in prior work. Now, for the question of diabetes as a vascular issue actually has been shown to affect a lot of different vascular related things, some of which I'm showing here. So the question is there a signal in the PPG waveform, potentially with a lot of the features that have been identified before, but likely also features that haven't been identified to predict diabetes. And so for that, we built user neural network to analyze data from a fairly large cohort, again, from Healthy Heart. I'll go through this quickly, but basically we had a primary cohort, standard train test dev split, and then we had two validation cohorts in addition to the holdout test set. One was simply a so-called contemporary cohort where we had PPG measurements from new patients enrolled after 2018. That was essentially after data lock and algorithm development. So we had 8,000 patients there. And then when this all started to look promising, we started prospectively enrolling a clinic cohort from 3 prevention clinics where we got around just under 200 patients and try to validate it there as well. So here are our high-level results. We had, for the remote data, that except for the clinic, basically, participants could measure their PPG as many times as they wanted, ultimately. And so we did 2 levels of analysis, one whereby we just look at every single recording labeled separately by the patient's diagnosis status, or whether we essentially averaged the DNN scores by the user. Generally speaking, the user level performance was better, which kind of makes sense because PPG is somewhat inherently noisy, especially when measured from a smartphone. And this was essentially our general discrimination at the user level was 0.76 in the test data set. Now, comparing user levels across the contemporary cohort, you can see it's pretty similar, a little degradation. Clinic cohort, we only had recording level. We didn't do it more than once. We probably should have, but we didn't. So we have to compare recording level. And here you can see the recording levels is pretty consistent. And then we cut this up in 1,000 ways, one of which was, what about people who presented to the clinic without a prior diagnosis of diabetes that then received an A1C or other, fasting serum glucose to diagnose diabetes, of which there's 164 patients out of the 181. And in this subset, the performance was still quite decent. So then in the primary cohort test data set, if we added easily identifiable things by self-report, by like age, gender, race, BMI, the AUC went up significantly to 0.83. This is sort of nested analyses with each one individually. And then we also had comorbidities like hypertension, hypercholesterolemia, which also coincidentally brought the AUC up to 0.83. So with some additional simple data, the overall discrimination went up quite high, or not relatively higher, I should say. But if you actually dig back and look at the literature for existing tests that are in common clinical use, AUCs are actually around like 0.7s to 8s for a lot of these, like pap smears and PSAs and whatnot. So it's just helpful to keep that in context. Now, interestingly, this certainly is worth further investigation, but we did see a significant linear association between the DNN score and hemoglobin A1C, as well as fasting glucose. Both were statistically significant for those who had it. This was heterogeneously obtained in healthy hearts, so it was only those who had it. But this is a post hoc subset analysis. And then in the clinic cohort, we did see a non-significant association, but the trend was the same, and the beta is also positive, so suggesting that it's also consistent there. And then just a couple things to highlight. Those that we got that had more than 6 recordings seem to generally have better performance. We looked at time of day. We looked at length of the recording. Notably, someone may ask, but we tried, but we did not exclude artifact or anything. So there was no signal pre-processing really being done other than really basic stuff. So the neural network effectively just learned to be robust to all those things. In order to try to get at a little bit of the mechanism as to how this was being done, we tried a couple of sensitivity analyses. So if we just used the R to R interval, so like essentially put a 1 on a vector of 1s and 0s at every peak over the length of the PPG, we were able to obtain an AUC of 0.72, which is actually pretty close to the 0.76 that we ultimately got from at the user level. So that sort of suggests that most of the data is most of the information for diabetes as relates to PPG is likely in the R to R interval. So that kind of correlates. If we and the individual associations of heart rate and heart rate variability with diabetes were attenuated after including the PPG score. So that again sort of corroborates that idea. And then when we put in individual PPG morphologies, just a single morphology per record, we saw how that would do to predict diabetes, and the AUC was 0.69, so suggesting that relatively speaking, there's more information in the longitudinal R to R intervals than the single waveform, but there is indeed some information in the waveform itself that is likely contributing as well. And then of course we did do some explainability as well. Oh, I see. Yeah, we did some explainability. This is some plotting of some filters in some internal layers, where, as you can see, and it's kind of interesting that we're highlighting here where, as I said, we did not exclude artifact. This is likely some kind of artifact, and the orange and the blue both are some kind of artifact. And different filters seem to identify, for example, that like this filter honed in on the artifact, it looks like, right? And then some other filters basically ignored it. So we found that kind of interesting. So in conclusion for this paper, and I'll conclude the talk with this, that we showed that smartphone measured PPG can provide an independent and non-invasive digital biomarker for diabetes, validated in 3 different data sets. It certainly expands the utility of PPG because we don't currently use it clinically to do this. Although, yeah, so it expands the capability of this currently available test that is actually in every healthcare system pretty much, at least in the US and the Western world. And given that we can obtain this, we show that we can obtain this from a smartphone, this potentially lowers barriers to access. And amongst the 224 million people or so that are undiagnosed worldwide, if this could be disseminated, there could, this could potentially move the needle with regard to helping folks identify when they have prevalent diabetes. So may have particular impact in underserved populations. So in conclusion, there's a whole bunch of data in medicine. I think everyone on this call here is excited to apply analytic methods broadly to try to make better sense of these different types of varied and complementary modalities of data. And ultimately, in addition to assisting with established diagnosis, helping us do our jobs better with that data that we already use it for, I think this idea of driving new insights is very exciting and also a very promising area for applying AI into medicine. So these are mentors and collaborators without which I would not be where I am. So much gratitude there. And thank you for your time and attention. Open to any questions.
Geoff, thank you so much for this whirlwind talk. I know that usually it takes a couple of seconds for people to get their thoughts together for questions. So I'll probably start with one.
Yeah.
A big thing in dermatology has been the issue of kind of skin pigmentation. And I know that there's a lot of literature, particularly in pleth, where there's biases in terms of, let's say, the oxygen saturation based on how much pigmentation there's in the skin.
Yep.
Could you talk a little bit about, like, I know that it looks like in your analysis, race did contribute additional information. What's the kind of the cohort kind of breakdown, and is that kind of encoded also in the amplitude information, or do you think that washes out when you kind of essentially normalize it by mean and standard deviation?
Right. Yeah, that was a great question, and something that we didn't quite have enough essentially ethnic diversity in healthy heart in this particular cohort to look at. So we did, I think most of the patients, if I recall, because we looked at this, were Caucasian or participants in the study, or in this subset particularly of the data. So we didn't really have that ability to look at specific races and skin pigments, but certainly very valuable and something we should do. Azumio, so Azumio is the partner that made that app. It's the instant heart rate app that's freely available on the App Store, and is I think it's the most used heart rate app or something. So we partnered with them for this study, and they have since just recently, I think last month, put out a diabetes prediction app as well. And so therefore are gathering data, based on this work, but they recently put it out last month. So they're gathering information as well on different skin pigments, et cetera.
I'm a little curious if there's been any, this is probably a broader or more random question, but with regards to stuff along the lines of like that company implementing the work that you did with the diabetes prediction, has there been any of the various predictions you've looked into, has there been any follow-on? What does it look like in practice, the application of the machine learning tool? How does it actually perform?
Yeah.
The analyses there.
Yeah, so that's a great question, and that's really the next stage. So we're actively in the process of designing and hopefully funding this, the prospective clinical validation for this work. And we're working with Azumio and this other potentially a couple other groups to try to do that. So that maybe next time I come back we'll have something to talk about more. But yeah, it's a great point that it's that prospective clinical validation that I think is what's going to be critical, right? Because we're all developing a lot of fun things, but we need to make sure that they generalize and show value clinically. Yeah.
Great. Well, I definitely want to keep the floor open if anyone else has other questions.
I have one question. So great talk, very interesting. Geoff Sonka here from Cedars. So I noticed this word interpretable in your paper, but I didn't quite catch like there is something was there about it, but can you like a little bit more explain how you interpret these findings of AI on the ECG, exactly how you use, how this is done?
Sure. Yeah. Now that you mention it, I'm realizing there's some inherent assumptions I made in making that statement, which I didn't realize. And I think what those assumptions is that this understanding that, at least to most physicians, cardiologists, that there is meaning associated with some of those segments, with all of those segments. Whether we understand all the meaning, or whether we understand all the segments or features in the ECG that are important, is an open question, and most likely the answer is no. We don't understand all the meaning and we don't understand all the features. But there is a standard lexicon of what does the PR segment mean physiologically. It's the time that it takes for the electrical signal to get from the atrium to the ventricle. What does the QRS duration mean? It's the time that it takes for the electrical signal to get from the AV node down the His-Purkinje system through the ventricles, right? And so each one of those segments that we a priori segmented the ECG into and forced our model to use as discrete elements have meaning associated with them. And so by virtue of getting a list of important features that the model used to make this prediction, it inherently suggests that, the PR interval in lead 2, which is a specific, or V2, which is a specific lead on the chest and may capture electrical activity from a certain structure portion of the heart, there's meaning that can be attributed to it from that lexicon that we understand. Does that help? Does that make sense? So, however, I think it's helpful to maintain an open mind that there might be meaning that we don't understand beyond that standard lexicon.
So if I understand correctly, you highlight the particular segment in ECG in kind of, if you were to show it to the physician on a case, right? You would highlight the particular segment in the ECG.
We could.
Responsible for that. Okay.
We could, yeah.
But you haven't done it, right? Or have you?
Well, ultimately, from an analysis standpoint, what we get is a list of variable importances.
Okay.
And so, as I showed in some of those figures, like it's trivial then to plot that, to use it to highlight the ECG, the segment ECG.
Is that importance feature? Is that for the group or for the individual ECG?
That's for the individual ECG.
Okay.
Yeah.
So what?
That can be, we also then can derive it for the group. Oh wait, actually, hang on. No. It's for the group. I apologize. It's for the group. Yeah. Okay. So for the disease, right?
Okay.
Yeah.
Okay. Yeah. Got it.
This is Konrad Pieszko from Dr. Sunka's lab. I have one question regarding this PP and diabetes study. Is there any relation between the output of your model and severity of diabetes, for example, measured by the levels of glycated hemoglobin? Is it, did you go in this direction?
Yeah, it's a great question. So if I understand correctly, the question is was there an association effectively between the model and diabetes severity? Is that right?
Yes. If the scores correlate with diabetes severity.
Right. So I think the main thing that suggests that there is